In this video, I'll provide an overview of Azure's high-performance compute storage options and how to optimize your Azure machine learning storage to reach your model's performance goals with the Microsoft for Startups dedicated GPU cluster. Azure offers several high-performance storage options for AI workloads with different price-performance trade-offs to help you scale to larger datasets during model training. Azure Blob Storage is the recommended and default storage option for Azure Machine Learning HPC AI workloads for massively scalable and secure object storage. You can optimize your costs with tiered storage for long-term data and flexibly scale up to massive datasets with a premium option for lower latency. Standard blob storage is going to offer the best price performance for most training workloads, but premium blob storage is a better solution for high transaction workloads, such as training with small to medium image and video files. Azure Premium Files offers lower latency for IOPS heavy workloads at a higher cost. Previous startups on the GPU cluster that have worked with audio files have utilized this option. Azure NetApps Files provides even higher IOPS, a greater range of supported protocols, and among the lowest latency, along with more data management capabilities such as snapshots, cross-region replication, albeit at a higher price point. For startups pushing the boundaries of compute and associated data scaling, Azure also offers Azure Managed Lustre, which has the largest throughput capacity per terabyte at low latency. You can mount Azure Managed Lustre to your Azure ML compute clusters, as well as connect to Azure Blob Storage for high performance processing of blob data, as well as for archiving process data into tiered blob storage for cost management. This is the top tier performance option for startups working with large life sciences, climate, or multimodal data sets at 100 plus terabytes. Lastly, Azure also offers a robust storage ISV partner ecosystem as well, such as Kumlo, Dell Apex, and Weka, that give you additional price performance options for AI HPC workloads. These are available for purchase and deployment through the Azure Marketplace. My key takeaway is that Azure offers a wide range of first-party and partner storage options with varying costs, capacity, bandwidth, IOPS, and latency trade-offs for your consideration. To set a common foundation for guidance on optimizing and troubleshooting Azure Machine Learning storage, I'll cover how jobs access data in Azure Machine Learning. Azure Machine Learning storage natively supports direct connection with data stores such as Azure Blob Storage, Azure Storage Account file shares, data lake storage, and SQL databases. When you submit a job, the Azure Machine Learning Data Runtime by default controls the data load from the storage location to the compute target. The Azure Machine Learning Data Runtime is written in Rust and optimized for speed and efficiency for machine learning tasks, with features including parallel data loading, CPU data prefetching for higher GPU utilization, and integration with FSpec to access local, remote, and embedded file systems. If you do want to use your own data loading and accessing code, for example, to have a Spark or Ray job read directly from storage URIs, then you can use direct mode, but then just make sure it's your responsibility to manage data access credentials in the setup. When you provide a data input output to a job, you must specify a path parameter that points to the data location. The top table on the slide shows the different data locations and example path parameters that Azure Machine Learning supports. While Azure ML doesn't provide direct integration with Azure HPC file storage options such as Azure NetApp Files or Azure Managed Lustre, you still have the flexibility to mount these file systems to your job container by chaining together a bash script and your training code. I included a minimal sample on the slide for mounting Azure Managed Lustre to an Azure ML CLI command job container to help you expand the price performance options you can explore with Azure ML. The Azure ML Data Runtime also provides several different data access mode options for accessing the local SSD disk on your compute target, outlined in the second table on the slide. Of particular importance to your distributed GPU training job is the selection between mount and download mode. Download input copies all of the data to the local hard drive before beginning the beginning of training. This method works best when your data set is small enough to fit on disk. For the GPU cluster, this corresponds to about 1 to 1.5 terabytes based on the job container memory net of your model without interfering with any other training. If you'll be iterating over a data set multiple times randomly, such as you're training on a CSV file, this will also be a better choice to go with download. In contrast, mount mode uses a Linux fuse to create an emulated file system to your data storage location to stream data to your job container. Mount works best for large data sets that don't fit on your GPU cluster local disks, but does require you to tune your code's data access behavior to maximize network and storage throughput. Make sure to tune your mount cache and disk settings for optimal GPU utilization to match your data access patterns and file sizes. There is an example in the lower right of the slide for tuning data access settings via environment variables in your job control script. Review the guide, Access Data in a Job for additional details on download and mount storage settings recommendations for handling large text, image, and video/audio datasets. Now we will transition to discussing the data loading flow in Azure Machine Learning jobs and Azure AI Storage Guidance. To optimize data loading performance in Azure ML distributed GPU jobs, it's important to understand the data flow within jobs. This diagram shows the four-step data flow between Azure Blob Storage and your A100 GPU instance. First, your cluster instance CPUs request data blobs from storage or a file system in parallel. Second, data is downloaded to the local SSD storage via the network interface card. Third, your cluster instance CPUs read the data for the pre-processing tasks in your data pipe to convert data into tensors. Fourth, these mini batches of tensors are read onto the GPU. What this data flow tells us is that there's several factors related to data that can influence how quickly you can train your model, including data location, storage choice, neural network size, file size, and the efficiency of client code accessing storage. There are heaps of data loading performance optimizations covered in the guide, Efficient Data Loading for Large Training Workloads, that I highly recommend reviewing after this video. There are 3 big performance gains I would recommend from this guide. First, make sure to co-locate your storage and compute in the same Azure region to avoid data transfer costs and network overhead. If your data is stored in a different region to your Azure ML workspace, then we recommend copying the data to a storage account in the same region using the AZ copy utility. AZ copy uses server-to-server APIs, so data is copied directly between storage servers rather than over network. Second, choose the right storage for your dataset. Azure ML supports direct database and data lake connections, but generally prefer Azure Blob Storage for large or evolving datasets. Use HDD for large files like images, and video and SSD for smaller files and or those with higher transactions. Do keep in mind each GPU instance has 24 gigabits per second bandwidth limit. So if you're over 6 nodes, make sure to file a support request for a mount storage quota increase. Your GPU instance has 36 terabytes of local storage. So if your dataset can fit and it's static, consider downloading your dataset to your instance disk instead for higher performance. There are more details on this covered in the guide linked on the slide, Efficient Data Loading for Large-Scale Training Workloads. Lastly, leverage the Azure ML SDKs for performant parallelized data reads over the native Azure storage APIs. Prefer download for faster training times if your dataset can fit on disk, but if not, choose mount and make sure to tune your cache and disk settings. To troubleshoot data loading bottlenecks and distributed GPU training jobs, start by diagnosing the problem and tuning the appropriate resource and or environment variables. Use the Azure portal account metrics tab to view and plot metrics like success end-to-end latency and success server latency. If you notice low data throughput but high success rates and low latency, you likely have limited compute threads. So consider increasing environment variables like the rslex download threads if downloading. And for mount mode, look at the environment variable dataset mount read buffer block count and dataset mount read threads to increase the number of compute threads. If metrics show low success end-to-end latency and success show both low success end-to-end latency and low success server latency, but there's high client latency. Check if the number of threads for mount/download is too low relative to the available cores and adjust accordingly. Also ensure the retry count for downloading isn't set too high as well. Monitor compute target disk I/O and usage from the Azure Machine Learning Studio's monitoring tab. If the disk is full, your code might be writing files to disk instead of output folders. For mount mode, set a TTL on cache data, so the environment variable dataset mount attribute cache TTL to keep compute nodes healthy. Review the Troubleshooting Data Access Guide for more tips and contact your Microsoft for Startups account team or Azure support for further assistance. These steps will help you maintain high utilization over the course of your Azure ML distributed training jobs to make the most of your GPU cluster reservation. In the next video, we will look at best practices and troubleshooting tips for optimizing Azure ML compute.